Imagine the universe compressed into a tiny, incredibly hot and dense speck, smaller than an atom. This speck, containing all the matter and energy we see today, suddenly explodes outward. This explosion, known as the Big Bang, marks the beginning of our universe as we know it. As the universe expanded and cooled, energy condensed into particles, forming the first protons, neutrons, and electrons. These particles eventually combined to form the first atoms, primarily hydrogen and helium, the building blocks of stars and galaxies. Observations of the cosmos revealed a remarkably uniform temperature across vast distances, posing the horizon problem. This led physicists to propose revolutionary ideas, including the theory of cosmic inflation, to address these cosmic conundrums. The horizon problem emerges from the finite speed of light. The cosmic microwave background, CMB radiation, shows that the universe was incredibly uniform in temperature just 380,000 years after the Big Bang. How could these regions, seemingly disconnected since the beginning of time, have reached such an even temperature? The horizon problem challenged the conventional Big Bang model and prompted the search for a more complete explanation. Another challenge to our understanding of the early universe came from the geometry of spacetime. General relativity tells us that the presence of matter and energy warps the fabric of spacetime. Measurements of the universe's geometry, particularly from the CMB, indicate that our universe is remarkably close to being flat. This flatness poses a problem because, according to the standard Big Bang model, any slight deviation from perfect flatness in the early universe would have been amplified over time. The universe's current near-flatness implies an extraordinarily fine-tuned initial state. This fine-tuning, known as the flatness problem, seemed highly improbable. It suggested that something fundamental was missing from our understanding of the universe's earliest moments. In the early 1980s, physicist Alan Guth proposed a revolutionary idea that addressed both the horizon and flatness problems, cosmic inflation. This theory posited that the universe, in the first fraction of a second after the Big Bang, underwent a period of exponential expansion. During this inflationary epoch, the universe expanded at an extraordinary rate, far faster than the speed of light. Cosmic inflation elegantly solves the horizon problem by proposing that the universe was much smaller than we thought before this rapid expansion. Similarly, cosmic inflation stretched the universe, driving its geometry towards near-perfect flatness, explaining the observations we see today. By the late 1970s, cosmology faced significant challenges. The horizon and flatness problems suggested that the conventional picture of the early universe was incomplete. These challenges led to a period of intense theoretical exploration within the cosmology community. This search for a more satisfactory explanation paved the way for the revolutionary idea of cosmic inflation. In 1979, physicist Alan Guth stumbled upon a possible solution to the cosmological conundrums while exploring grand unified theories. Guth proposed that the early universe might have been trapped in a false vacuum, a metastable state with a high energy density. This false vacuum would drive an exponential expansion of spacetime. Guth's initial model faced a significant challenge: how to end inflation gracefully and transition to the more familiar, slower expansion of the standard Big Bang model. To explain the dynamics of cosmic inflation, physicists introduced the concept of the inflaton field, a hypothetical scalar field that permeated the early universe. In the simplest inflationary models, the inflaton field is initially trapped in a false vacuum state. As the universe expands, the inflaton field slowly rolls down the potential energy curve, triggering the decay of the false vacuum. This energy release marks the end of inflation and reheats the universe, setting the stage for the formation of the particles and elements that make up our universe today. Guth's original model of inflation faced the graceful exit problem. Physicists, including Andre Linde, Andreas Albrecht, and Paul Steinhardt, developed alternative models, known as new inflation or slow-roll inflation, that addressed this issue. These new models introduced refinements to the shape of the inflaton potential, allowing for a smoother transition to the standard Big Bang cosmology. Despite these refinements, inflation remained a highly speculative idea in its early years. Imagine a universe smaller than an atom, suddenly embarking on a growth spurt of unimaginable proportions. During this brief but dramatic epoch, the universe expanded by a factor of at least 10 to the power of 26. This rapid stretching of spacetime is driven by the negative pressure of the inflaton field. This exponential growth is a direct consequence of Einstein's theory of general relativity. The horizon problem arises from the finite speed of light and the vastness of the observable universe. Regions of the cosmic microwave background radiation, CMB, should not have had time to interact since the Big Bang. Yet the CMB exhibits a remarkable uniformity in temperature across the entire observable universe. Cosmic inflation provides an elegant solution to this conundrum. Before inflation, the universe was much smaller, allowing all regions to be in close contact and reach a uniform temperature. The flatness problem arises from the observation that the universe's geometry is remarkably close to being flat. According to the standard Big Bang model, any slight deviation from perfect flatness in the early universe would have been amplified over time. Cosmic inflation resolves the flatness problem by dramatically stretching the fabric of spacetime. During inflation, the universe's rapid expansion smoothed out any initial curvature. The exponential growth of inflation effectively diluted any initial curvature, explaining why the universe appears so flat today. Inflation provides an elegant solution to the horizon and flatness problems and leads to a profound implication. Quantum fluctuations during the inflationary epoch were stretched to cosmological sizes. These density variations acted as gravitational seeds, growing into the galaxies and large-scale structures we observe today. Inflation connects the quantum world to the largest scales of the cosmos, providing a mechanism for generating the seeds of structure from the inherent randomness of the quantum realm. Cosmic inflation, for all its elegance in resolving cosmological puzzles, would remain a compelling yet speculative idea if not for its testable predictions. Fortunately, inflation leaves its fingerprints on the cosmos, subtle patterns imprinted on the cosmic microwave background, CMB radiation, the faint afterglow of the Big Bang. These patterns serve as a cosmic echo chamber, carrying whispers of the universe's earliest moments. Remember those quantum fluctuations, stretched to cosmological scales during inflation. These tiny density variations, the seeds of galaxies and large-scale structure, also left their mark on the CMB. As the universe cooled after the Big Bang, these density variations translated into minute temperature differences in the CMB, creating a mottled pattern of slightly hotter and colder spots. These temperature fluctuations, though incredibly faint, just a few parts in 100,000, have been meticulously mapped by space-based telescopes like Planck and WMAP. The observed pattern of these fluctuations, their size and distribution across the sky, provides a powerful test of inflationary cosmology. Remarkably, the observed CMB temperature fluctuations align beautifully with the predictions of inflation. The specific pattern of these fluctuations, their statistical properties, provides strong evidence for a period of rapid expansion in the early universe, lending credence to the theory of cosmic inflation. The cosmic microwave background radiation holds even more clues to the universe's inflationary past. Besides temperature fluctuations, inflation also predicts the existence of primordial gravitational waves, ripples in the fabric of space-time generated during the universe's exponential expansion. These gravitational waves, unlike the electromagnetic waves we detect with telescopes, are disturbances in the very fabric of space-time, stretching and squeezing space itself as they propagate. While incredibly faint and challenging to detect directly, these primordial gravitational waves would leave a unique signature on the CMB, a specific pattern of polarization. Polarization refers to the orientation of the electric field of light waves. Just as sunlight reflecting off a lake can become polarized, with its electric field oscillating in a preferred direction, so too can the CMB radiation become polarized by scattering off electrons in the early universe. Primordial gravitational waves would create a distinct swirling pattern in the CMB's polarization, known as B-mode polarization. Detecting this B-mode polarization would provide smoking gun evidence for inflation and offer a glimpse into the universe's first fraction of a second, a realm of extreme energies and unimaginable conditions. The influence of inflation extends far beyond the cosmic microwave background radiation. Those tiny quantum fluctuations, stretched to cosmological scales during inflation, didn't just leave their mark on the CMB, they also seeded the formation of the large-scale structure we observe in the universe today. As the universe continued to expand and cool after inflation, those regions with slightly higher densities, thanks to those initial quantum fluctuations, exerted a slightly stronger gravitational pull on their surroundings. This gravitational attraction drew in more and more matter over billions of years, amplifying those initial density variations. Over time, this gravitational collapse gave rise to galaxies, clusters of galaxies, and vast cosmic voids, forming the intricate cosmic web we observe today. The distribution of galaxies across the universe is not random. It reflects those initial density perturbations, those seeds of structure sown during inflation. The statistical properties of this large-scale structure, the way galaxies cluster and voids form, provide another independent test of inflationary cosmology. And once again, the predictions of inflation align remarkably well with observations, further solidifying its role as a cornerstone of modern cosmology. Cosmic inflation, while profoundly successful in explaining key features of our universe, also leads to a mind-boggling implication: the possible existence of a multiverse, a vast ensemble of universes, each with its own unique properties and laws of physics. In some inflationary models, known as eternal inflation, the inflationary process doesn't end everywhere at the same time. Instead, inflation might continue indefinitely in some regions of space-time, while in other regions, like our own observable universe, inflation ends, giving rise to a bubble of space and time where stars and galaxies can form. This process of bubble universe formation could occur repeatedly, with different regions of space-time exiting inflation at different times, leading to a vast and ever-expanding multiverse. Each bubble universe within this multiverse could have its own unique set of physical constants, laws of physics, and even dimensionality. The concept of the multiverse, while highly speculative and currently beyond the reach of direct observation, remains a topic of intense theoretical debate and exploration. If true, it would profoundly alter our understanding of our place in the cosmos, suggesting that our observable universe is but one of countless cosmic islands within a vast and unimaginably diverse multiverse. The vastness of the cosmos raises a profound question. Why does our universe possess the specific set of physical laws and constants that allow for life? This delves into the Anthropic principle, the idea that the universe's properties must be compatible with our existence. In a multiverse, countless universes exist with different laws. The Anthropic principle gains new significance. We find ourselves in a universe fine-tuned for life due to selection bias. Imagine a cosmic lottery where each ticket represents a different universe. Only a tiny fraction of these tickets would support life. We hold one of those winning tickets, not by design, but because we couldn't exist otherwise. The Anthropic principle raises philosophical questions about fine-tuning, chance, and the limits of our understanding. The concept of the multiverse, while still highly speculative, has captured the imagination of physicists and cosmologists, leading to intense theoretical exploration of its implications. One intriguing idea that has emerged from this exploration is the concept of the cosmic landscape. In string theory, a leading candidate for a unified theory of physics, the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. The way these strings vibrate determines the properties of particles and forces we observe. String theory, however, allows for a vast number of possible solutions, each representing a different set of physical laws and constants. This vast landscape of possible universes, often visualized as a complex and rugged terrain with mountains, valleys, and plains, represents the cosmic landscape. Each point in this landscape corresponds to a different universe with a unique set of physical parameters. Our universe in this picture occupies just one small region of this vast landscape. The cosmic landscape provides a framework for understanding the diversity of universes that might exist within the multiverse. It suggests that the physical laws and constants we observe are not necessarily fundamental, but rather represent a particular solution, a particular point in this vast landscape of possibilities. Cosmic inflation, once a radical idea, has become a cornerstone of modern cosmology, providing a compelling explanation for key features of our universe and opening up new avenues of exploration into the universe's earliest moments. But the story of inflation is far from over. Cosmologists continue to refine inflationary models, seeking to understand the precise mechanism that drove inflation, the nature of the inflaton field, and the implications for fundamental physics. The quest to detect primordial gravitational waves, those faint ripples in space-time generated during inflation, remains a top priority. Finding these gravitational waves would provide definitive proof of inflation and offer a glimpse into the universe's first fraction of a second, a realm of extreme energies and unimaginable conditions. Moreover, studying the detailed properties of the cosmic microwave background radiation and the large-scale structure of the universe provides increasingly precise tests of inflationary models, allowing cosmologists to distinguish between different scenarios and refine our understanding of the universe's infancy. The future of cosmology is bright, fueled by technological advancements in telescopes and detectors, as well as theoretical breakthroughs in our understanding of gravity, quantum mechanics, and the fundamental nature of the universe. Inflation, with its profound implications and testable predictions, will undoubtedly continue to guide us on this grand journey of cosmic exploration. Cosmic inflation, with its mind-boggling implications of a vast and potentially diverse multiverse, challenges our perception of our place in the cosmos. It suggests that our observable universe, vast as it is, might be just one of countless cosmic islands within a much grander and more complex reality. This realization inspires a sense of awe and humility. Awe at the sheer scale and grandeur of the cosmos, a universe far stranger and more wondrous than we could have imagined. Humility in recognizing our limited perspective, our existence confined to a tiny corner of a potentially infinite multiverse. Yet, amidst this awe and humility, there's also a profound sense of wonder and excitement. The quest to understand the universe, to unravel its mysteries and decode its secrets, is a journey that has captivated humanity for millennia. Cosmic inflation, with its profound implications and testable predictions, has breathed new life into this quest, providing us with powerful tools to probe the universe's deepest secrets. As we continue to explore the cosmos, guided by the light of reason and driven by an insatiable curiosity, we embark on a journey of discovery that transcends the boundaries of space and time. connecting us to the grand narrative of the universe, from its fiery birth to its ultimate fate, a journey that reminds us of the power of human ingenuity and the enduring spirit of exploration that lies at the heart of our existence. The theory of cosmic inflation, from a bold hypothesis to a cornerstone of modern cosmology, represents a remarkable triumph of human ingenuity. Inflation's elegant solution to the horizon and flatness problems, and its agreement with cosmic microwave background observations, have elevated it to a well-supported theory. The universe, as revealed by inflation, is far stranger and more wondrous than we imagined. Inflation has altered our cosmic perspective, unlocking the universe's deepest secrets. While cosmic inflation has revolutionized our understanding of the universe, it's just the beginning of our cosmic exploration. The quest to understand inflation's mechanism and the possibility of a multiverse drives research. The hunt for primordial gravitational waves promises a glimpse into the universe's first moments. Advancements in telescopes and detectors push the boundaries of our knowledge, bringing us closer to answering profound questions. The study of cosmic inflation has profound implications, challenging us to confront the vastness of the cosmos. As we explore the universe, guided by reason and curiosity, we connect to the grand narrative of the cosmos. The story of cosmic inflation is a testament to human imagination and our quest to comprehend the universe.